This video is going to cover two scenarios where we use the DMF formula on page 40 of the notes. And also, we will use the transmissibility formula, which is on page 49. For case A, the transmission of forces to the base. So let's look at, first of all, example 4 in the notes, where we have an air conditioning unit resting on top of two beams. And you know the midspan stiffness of each beam being K. So we're trying to push two beams down at the same time. So the total stiffness is twice of that, where EI and L belong to each individual beam. And we have this air conditioning unit producing a sinusoidal force of this magnitude and driving at big omega being 300 revolutions per minute. And be careful to translate that into radians per second as big omega. So this is a typical situation where we use the initial formulas in this chapter. Let me show you again. 40, page 40, where the steady state response is found as rho, a constant, times a sinusoidal function of big omega t minus phi phase angle. And rho can be compared to the static deflection, and this ratio is fixed as a function of beta and zeta, both being dimensionless ratios. So we're going to use this formula now to solve our problem. Let's recap. We've got the stiffness, and we're going to use stiffness and mass to compute omega 0, the natural frequency, and then we'll compute the beta ratio, frequency ratio, and also we're given the damping at, let's see, well, we're given the damping as 1% viscous damping here, and we then can find out the amplitude of the steady state midpoint deflection, which is rho. So it goes like this. I'm going to do it slightly out of the original order to see what the difference is, and also to see that we get the same solution. Okay, so in the notes, I first put in all the numerical values, including those for zeta and beta that appear in this rho formula, and then I compute what is rho going to be, which is the steady state deflection, and I convert it to millimeters. But here I'm going to first enter the formula for DMF because we are going to use it a lot in this chapter. So this is the formula for DMF in symbolic form. Okay. Beta is the frequency ratio and zeta is the damping ratio. Then I'll put in all the numbers. Okay. Mass is equal to this much in kilograms. You can put in multiple input along one line by separating them with colons. So this is the Young's modulus or elastic modulus. It is in bigger units, so 10 to the 9 is a giga. And here's I, moment of inertia, 4.16 times 10 to the negative 6. So we can write it as 1 over 10 to the 6th power. That's a meter to the 4th power. And then the length of the beam, each beam is so be careful here. You've got to use colon equal to assign numbers to symbols. You call them 438 meters. Okay, so now we are able to compute our stiffness of the two beams together. So that's 2 times the standard formula for the midspan stiffness, 48 EI. Now be careful, it's not EI, but E times I. And you notice that each character appears in boldface. That means that something has been stored in it, over L cubed. So that is our stiffness. Now let me enter the given damping ratio at 1% and the driving force. Okay, be careful here. Colon separates one input from another. P0, the driving force magnitude, is colon equal to this much in newtons. And then big omega, colon equal to, it's given as 300 revolutions per minute. So be careful. First, translate that to radians. So multiply by 2 pi to convert a revolution to a radian. And then it's given as a per minute quantity, so it's per 60 seconds. And now this thing is in radians per second. All right. Now that we have big omega, we can compute small omega, or small omega 0. That's the natural frequency of the mass spring damper system. That is the square root of k over m. And then we compute the frequency ratio, beta, being big omega over omega 0, the natural frequency. All right. Now let's take a look at our DMF again. Notice that it's been updated automatically. Excuse me, because I have a throat problem today. So finally, this DMF is the multiplication factor to the static deflection to get the dynamic deflection. So rho, or you can call it R, is equal to P0 over K, that's the static deflection, times DMF. It's rather small, it's in meters. So at this point, you can just simply type in multiply. It says answer. Okay, so what I did, let me do that again. If I just press multiply key, it understands that I want to do something with the previous answer. So to 1000 turns it into millimeter units. So it's about 0.052 millimeters of deflection in the dynamic case. Let's move on to example 5 about transmissibility. In this case, we have a 29.5 kilogram machine on 3 springs. They have equal stiffnesses, K, which is the unknown in this problem. And you're asked to design for K. Let's look at the parameters. The machine runs at 580 revolutions per minute, and we require that only 10% of this total shaking force can be transmitted to the supporting base. So how stiff should each spring be? That's K. So in this case, we are going to use the transmissibility formula, which is here. And you can refer to page 49 for that formula again. Okay, this is the situation. We have some machinery running on top of the fixed base, and the total base force experienced compared to the applied force P0 is this ratio here, which again involves the DMF, it's the D part, but further multiplied to a square root of this thing. So let's see how we can make use of what we have already done. So the total maximum force is going to be just D times a square root of all this multiplied to the driving force P0. And the DMF I already have. So if you're working already like me, you have this, you can copy it. I would suggest that you start a new file. Okay, so document, insert, a new problem, not page. Okay, a new problem forgets everything that you have done previously, but you can still copy and paste. Because if you take a look at B and Z, there's no value. It's a clean symbol. So don't forget, this is the BMF part, the D part, but the transmissibility is small. So let's enter that. The transmissibility colon equal to the DMF times this further factor of square root of 1 plus 2 times beta squared. So we have the transmissibility now. So again, I'm doing things slightly out of the original order in the note, and you can see the difference. So it stays symbolic. That's the transmissibility formula. In fact, I would suggest that you save it, okay, as some file on your handheld or PC or tablet, so that next time you have similar problems, you can just open this file. I would suggest that you save it now while everything is still clean without numerical input, and just use it next time. Okay, whatever saved up to this point, and nothing more should be saved. Okay, for the generic template that you're going to use for next time. So now I'm going to enter all those numerical values for this particular problem. The mass, first of all, light machine, and then omega, the driving frequency, is 580. That's in revolutions per minute. So per second is this multiplied to 2 pi. Now, let's look at omega 0, the natural frequency. That is square root k over n. So we'll just enter that, but be careful. K is the total stiffness of your structure, which in this case consists of 3 springs. So 3k, 3 times k over n. Of course, k is going to stay symbolic. That's the unknown we have that we're going to solve for. And beta, finally, the frequency ratio is big omega, the driving frequency, over omega 0, our natural frequency of the structure, which is a function of k. So now if you take a look at the transmissibility, again, it turns into a function of k. Now what is the requirement here? We want this thing to be no more than 10% as required. Okay, 10% of this total shaking force can be transmitted to the base. So we're going to have to solve an equation like this. Transmissibility is going to be less than, let's say, 1. That is the given requirement. And we solve for that. Let's just try to solve it naively and see what happens for k. It actually gets stuck. And here you see it doesn't work. Right, so you need to give it some more information. So the crucial information here is that k is greater than 0. Here it doesn't work. Why is that? Because you see z is here, and we forgot to put in a numerical value for z. So this is too complicated to solve. So I'm going to show you some of the mistakes so that you don't make it. Okay. So you see here, before I solve it, I have to substitute the value of z into this expression so that it turns out to be just a function of k. Then I can do the solution. And this requires a bit more care to do, because what we're going to do is or with the substitution that z equals some number. Let's first look at the zero damping case. But if you enter like this, you're going to get an error message as well. So let me show you that also. This gives you some kind of syntax error. Why is that? Because this makes no sense. Z equals 0 less than 0.1. What do you mean by that? Okay, so it's really the transmissibility in the particular case where Z is equal to 0, all that as a function of K has to be less than 0.1. Okay, now you should be able to solve it. And it gives you the value, the range of K, to be anywhere from 0 to about 3.3 kilonewtons per meter. Okay, so now everything is smooth sailing from here. For different cases mentioned in this problem, negligible or 5% or 20% damping, you just copy and paste. Okay, let me show you again. Copy and paste by arrowing up. And use the arrow to go up if you're using the handheld, and enter to bring it down again. And you just go ahead and change the given numerical value for the damping ratio to, let's say, 0.05. That's 5% damping, and solve. So in this case, A can go up to about 3,200, 3,100 kilonewtons per meter. So similarly, and solve for the case where we have a 20% damping just by changing this number to 2. Sure. You get a new range of suitable stiffnesses.